Welcome to the Explainer. Okay, I am absolutely thrilled to get into this one today because we're about to decode the terrifying, violent, and honestly utterly beautiful life cycle of the universe's most massive objects. We are going to look at how stars are born, how they operate, and the absolutely mind-bending physics of how they die. Really, this isn't just astronomy we're talking about, it's the ultimate story of creation and annihilation.
Right off the bat, to really wrap our heads around this topic, we have to establish the sheer, incomprehensible scale of the cosmos. Just think about the number 100 billion. In our galaxy alone, the Milky Way, there are over 100 billion stars. And if that doesn't make your head spin, consider that there are over 100 billion galaxies in the observable universe. There are literally more stars out there than there are specks of sand on all the beaches on Earth. Most of them are so incredibly far away, they just look like faint little dots. But the sheer volume of stellar activity happening right this second is staggering. And this quote right here brilliantly illustrates why all of those billions of stars actually matter to you and me. Everything, every atom in our bodies was once part of the pre-solar nebula. You see, understanding the violent, chaotic lives of stars is actually the key to understanding our very own origins. The iron in your blood, the calcium in your bones, all of it was literally forged in the fiery bellies of ancient dying stars. So, to understand them is to understand us.
All right, let's dive into Section 1, the Cosmic Star Nursery. So, where does it all begin? Every single star starts its life in spectacular swirling clouds of dust and gas drifting through space, spanning billions of miles across. We call these cosmic star nurseries nebulas. You might actually know some of the famous ones, like the Orion Nebula or the Horsehead Nebula. Within these dark, dense pockets of gas, millions of new stars are currently being born, totally hidden away from the rest of the universe.
Now, before we get into how they're born, we need a quick reality check. We completely rely on our sun, right? It's a blinding ball of superheated gas, nearly 1 million miles in diameter. It feels incredibly massive to us, but when we compare our life-giving sun to a hypergiant like VY Canis Majoris, it's a completely different league. VY Canis Majoris is 1 billion times bigger than our sun. I mean, if you dropped it into the center of our solar system, its edges would extend all the way out past Jupiter. Our star is really just an average player in a very, very big game.
So how exactly do these massive stellar bodies actually come into existence? For a long time, the thick dust of nebulas kind of kept this a secret, but thanks to the infrared cameras on NASA's Spitzer Space Telescope, which can see heat directly through the dust, we finally have the recipe. And honestly, it's shockingly simple. You just need 3 things: hydrogen gas, gravity, and time. Gravity basically acts as a relentless vortex, pulling hydrogen dust and gas together over hundreds of thousands of years. As all this matter gets crushed into a smaller and smaller space, the temperature inevitably skyrockets. The young star is violently compressed, eventually hitting a mind-boggling 15 million degrees at its core, triggering a massive eruption of energy.
Okay, moving on to Section 2, the engine of life. Once a star is actually born, how on earth does it keep going? Up until the early 20th century, the greatest problem facing physics was figuring out what exactly fuels these massive objects. Because think about it, they produce staggering amounts of heat and light for billions, sometimes trillions of years. What could possibly be the engine driving that kind of stamina?
Well, it all boils down to a famous equation I'm sure you know: E equals mc squared. It took the absolute genius of Albert Einstein to unlock the secret of the stars. He proved that the engine isn't chemical, it's nuclear fusion. Deep inside the core, where gravity crushes hydrogen at 15 million degrees, the atoms are moving so wildly fast they literally smash into each other and fuse, creating a brand new element, helium. But here is the real magic trick. The resulting helium actually weighs slightly less than the original hydrogen. That missing mass doesn't just disappear, though. It gets converted into pure, unimaginable energy. And that pure energy takes the form of photons. Let me tell you, their journey is totally epic. After being forged deep in the star's core, these packets of light bounce around for hundreds of thousands of years before they finally escape. They're violently expelled into space during massive magnetic solar flares. From there, they shoot through the freezing vacuum of space at a blistering 186,000 miles per second, taking exactly 8.3 minutes to hit Earth. Trillions of these photons strike our planet every single second. They ignite photosynthesis, they drive our weather, and they power pretty much every biological process we know of. This starlight is, quite literally, the engine of life. But, as we know, nothing lasts forever. Which brings us to a slightly grim reality in Section 3, the death of our sun.
99% of stars, including our own beautiful sun, will eventually run out of their hydrogen fuel. And when that nuclear furnace switches off, gravity takes over, and the star begins its violent death throes.
So what exactly is that going to look like for us? Let's walk through the apocalyptic future of our solar system. First, as the core heats up desperately trying to survive, the sun's outer layers will bloat outward, transforming it into a massive red giant. It's going to expand so much that it will literally engulf Mercury and Venus. By the time it reaches Earth's orbit, it's going to act like a cosmic oven set to broil, absolutely boiling away our oceans and turning the surface into a molten hell. Eventually, the sun will just shed its outer layers entirely, leaving behind an Earth-sized white-hot core called a white dwarf. Its glowing outer layers will shine beautifully as a planetary nebula, basically a ghost of its former self, lingering for about 10,000 years before just fading into the dark. Now, our sun? It's going to go out relatively quietly. But what happens to the massive stars? We find out in Section 4. Monsters of the Cosmos. They don't just fade away. They run out of fuel, collapse inward, and literally bounce off their own cores in the biggest fireworks display in the universe, a supernova. And what's left behind when the smoke clears are the true monsters of the cosmos.
The first monster we have to talk about is the neutron star, and this is mind-bending physics at its absolute finest. When a massive star's core collapses, the gravity is so intensely powerful that it literally crushes the star's electrons and protons together until they merge into pure neutrons. Imagine taking a core with twice the mass of our sun and violently squishing it down to the size of a city like Manhattan. It becomes this hyper-dense pressure cooker. To put it in perspective, if you were to take just one single teaspoon of matter from a neutron star, it would weigh 1 billion tons on Earth. No way, right? It's almost impossible to comprehend.
And somehow, the physics get weirder. Because that massive core was forced to shrink down to city size so rapidly, it retains all its rotational energy, meaning it spins incredibly fast. We call these spinning neutron stars pulsars. As they spin, sometimes at up to 20% the speed of light, their chaotic magnetic fields generate lethal beams of radiation shooting straight out from their poles. If Earth happens to be in the path of one of these beams, we see it as a flash, pulsing like a cosmic lighthouse shining across the universe.
To truly grasp how fast these objects are spinning, wrap your head around this number, 700 revolutions per second. When a pulsar pulls in matter from a nearby object, it accelerates. It reaches a point where it spins hundreds of times in the literal blink of an eye. On Earth, a day takes 24 hours. On a millisecond pulsar, a day lasts a 700th of a second. It operates like the ultimate cosmic kitchen blender, slicing and obliterating anything in the path of its energy.
Now, as if a pulsar wasn't terrifying enough, roughly 1 in 10 neutron stars becomes something even more exotic, a magnetar. This is a rare, highly volatile cosmic anomaly. Magnetars possess the single most powerful magnetic field in the entire known universe. They are so ridiculously unstable that their twisting magnetic forces actually cause starquakes. They literally rip the crust of the dense neutron star wide open, spewing out massive bursts of high-intensity X-rays.
Just consider the magnitude of this force for a second. 1,000 trillion. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's magnetic field. This is an amount of magnetism that is frankly hostile to existence. If any normal object, say a spaceship or a planet, got too close to a magnetar, the magnetic pull is so violent it would literally tear the charged particles right from their atoms. It would instantly shred the molecular structure of anything in its vicinity.
All right, let's move to our final topic, Section 5, the Black Widow Pulsar. And I gotta warn you, this one really has the vibe of a true crime thriller. Up until now, we've talked about these monster stars in isolation. But what happens when one of these dead, spinning, radiation-spewing objects isn't alone? What happens when it's part of a binary system and has a sibling star right next door? Well, you get the absolute worst-case scenario in the universe.
Enter the Black Widow Pulsar. It's essentially an undead zombie star. And here is its cosmic rap sheet. When its companion sibling star naturally bloats up as a red giant, the dead pulsar begins to aggressively siphon off its gas. Feeding on its sibling, the pulsar accelerates its own spin to those terrifying millisecond speeds. And as it spins faster, its radiation beams reignite, and it blasts its sibling star, heating the companion to over 21,000 degrees Fahrenheit. That's twice as hot as our sun. Finally, it obliterates its sibling completely, eviscerating the very star that brought it back to life, leaving absolutely zero trace of evidence behind. It is stellar annihilation at its most ruthless.
So as we wrap up this explainer, I want to leave you with a provocative question to ponder. Knowing what we know now about the beautiful nebular nurseries, those life-giving photons, and the terrifying, violent ends of these giant monsters, next time you look up at the night sky, are you seeing a cradle of life or a stellar graveyard? You know, the incredible truth is, it's both. We are part of a violent, endlessly recycling cosmic ecosystem, and every single atom in your body is proof of that epic journey. Keep looking up and never stop wondering.